Alright guys, this is 3-2 in Advanced Algebra 2. We're going to refresh our memory about systems of linear equations, which we should have done a couple times before in our previous classes. If you graph two lines, if you graph two lines, only three different things could happen. Those lines could intersect at one place right there to where you get one solution, and in this case that solution is at 6, 3. It's just the ordered pair where they intersect at. Those lines could never intersect at all, meaning they were parallel to each other. And here's our two equations. You can tell those lines are parallel because they have the same slope, so that means that there's no solutions because we're looking for where these lines intersect and they don't intersect. So there's no solutions because there's parallel lines because they have the same slope. Or the other possibility is you can graph two lines that were what we call coincident. It was the exact same thing. Like this equation and that equation, if you put them both in slope-intercept form, you graph the same line twice. So that means they intersect each other everywhere, and that's called infinite solutions. But you have to be careful with that because there's not like an infinite amount of answers. Well, there is an infinite amount of answers, but there's also an infinite amount of wrong answers. It's like not every ordered pair makes that situation true. For example, 0, 0 right here is not even on that line because if you put 0 in for x, you'd get, and 0 in for y, you'd get 0 equals 3, and that's not a true situation. So we have to do this, what we call a college algebra type answer. There's infinite solutions in the form of, you know how points are always written, x comma y. Well, we're going to let x be x, and this right here is whatever y equals. And didn't we know that y equals 1/2 x plus 3? Meaning, if you pick whatever x value you want to, like, let's say 0 right here, then y would turn out to be, in this case, 3. So there's a solution. Or if you picked 2 for an x value, if we pick 2 for an x value and we substitute 2 in here, you get 1/2 times 2 and get 1 out of that, and y turns out to be 4 in that situation. So 2, 4 is a solution. And any solution in the form of x comma 1/2 x plus 3 will be on this line because this is what x is. You can let it be whatever. And this is what y is. It's 1/2 of x plus 3. So we'll kind of get better at that as this chapter goes along. So we're just going to refresh our memory here of how to solve these. There's three methods that we can solve linear systems by. And one's by graphing, and that's what they want us to do on our first guy. So we're going to make a class rule that says we're going to take each equation and put it in slope-intercept form first. So what I'll do is I'll subtract x from both sides, and this will turn out to be negative 3y equals negative x plus 6. And then, of course, we'll have to divide every term by negative 3. So that would become a positive 1/3 x minus 2. And then to solve systems by graphing, it's by far the worst method because we're so inaccurate with how we graph. So what we'll do is we'll plot as many points as we can on our first line that we're graphing. The y-intercept is negative 2. The slope is 1/3, so I'm going to rise 1 and run 3. Rise 1 and run 3. 1, 2, 3. Rise 1 and run 3. But I'm going to put as many points as I can. I'm going to go down 1 and to the left 3 just to make this line as accurate as humanly possible. 1, 2, 3. Then I'll take my straight edge and connect the dots together as best I can. There's the first line that we graphed. The second line we got to put in slope-intercept form also. So I'll subtract 2x over and then divide by negative 1, which changes all the signs. And now what I'm looking for is to get a green dot on top of a red dot. That's where I'm looking to get the system's solution at, if that even happens. I can tell that that's going to happen right now because these lines are not parallel to each other. They don't have the same slope, and it's not the same line, so it's not going to be coincident lines. So let me start here, and the slope is 2, so that's rise 2, run 1. But if I go this way, rise 2 and run 1, do you see how my green dots are like moving away from the red line if I keep going rise 2, run 1? I'd really like to get closer to the red line, so instead of going up 2 and to the right 1, how about we go down 2 and to the left 1, down 2 and to the left 1, down 2 and to the left 1, and bingo, I got a green dot on top of a red dot. You must finish this problem off by graphing the line. A lot of people just stop when they get the solution. That's not what the question was. The question was to graph both lines And now our solution right here is at the ordered pair of -3, -3. So we'll put that in our answer blank right here. There was one solution to this puppy. Our next guy, let's take our first equation, put it in slope-intercept form. That'd be y equals a -3x minus 2. There's still a bunch of you that aren't realizing you got to subtract 3x over. You got to do the opposite operation to get something over to the other side of the equal sign. Those are two amateur of mistakes at our level at this point. So be careful when you're doing this. -2, then down 3 to the right 1, down 3 to the right 1. And remember, on our first line, we're putting as many points as we possibly can so we can be accurate. So I'll just keep on sloping my slope. Straight edge, connect together. The second guy, time to put it in slope-intercept form. I get 2y equals -6x plus 10. Divide everything by 2. That'd be -3x plus 5. And I can tell with my experience that these lines have the same slope, and they have different y-intercepts also, so they're going to be parallel lines. So I know they're not going to intersect, but I still got to graph the line anyway. So that was at 5, and then go down 3 to the right 1, down 3 to the right 1. But I could search all I want to for a blue dot on top of a red dot. It's just not going to happen. So because I saw ahead of time that these were parallel lines, that means my answer is no solutions. Then you must state for me why, because we had parallel lines. Then you must tell me how you knew that. It's because they had the same slope. And please put the same slope in parentheses. So that's our answer. When there's no solutions, it's because those are parallel lines. And how did you know that? Because they have the same slope. That's the only way you know on a graph if lines are parallel, because they have the same slope. Next guy, let's take our top dude and put it in slope-intercept form. So we'd subtract x over. And my pen would put the minus sign, that'd be good. Then we'll divide by 2. And there's a -1 in front of x. We're going to divide it by 2, so that would give us a -1/2. And this guy's plus 5/2. Oh, yuck. That's not cool. So let's graph it. 5/2 is at 2.5. And I want to go down 1. Well, if I'm at 2.5, I'd go down to 1.5. And then to the right 2. Down 1 and to the right 2. So I'm got these little half increments that I'm kind of moving by. I keep going down 1 and to the right 2, and we're trying to put as many points as we possibly can on the first line. So I could also go up 1, which would put me up to 3.5, and to the left 2, up 1 and to the left 2, and just keep on keeping on. The more points you put on it, the more accurate you get, because we're going to look for a dot on top of a dot, if you will. And then next guy, I want to get y all by itself. Well, y, the term with the y is all by itself, so I could just divide everything by -6 if I go old school baby steps, because this would turn out to be a -1/2 x. And then a negative over a negative is a positive. 15/6. 3 goes into each one of those. 3 goes into 15 5 times. 3 goes into 6 twice. And remember, this came out positive because we had a negative over a negative. And that would be what y equals. So you can see that these are the exact same equation. You got y equals -1/2 x plus 5/2 if you like to have the y on the left, using a little symmetric property right there. And y equals -1/2 x plus 5/2. So I can graph the same thing again. It's all done. So this means that this has infinite solutions. Please spell infinite correctly. Infinite with an E at the end. But we have to say infinite solutions in the form of, and then we're going to write an ordered pair after this. The ordered pairs are always written x comma y. So we'll let x be x every time, but instead of putting a y right here, we're going to put what y equals. It's like the substitution property right here. Y equals a negative 1/2 x plus 5/2. Make sure you don't actually put y equals in here. It's just x comma y, but we know that y is negative 1/2 x plus 5/2, meaning there are an infinite amount of solutions, but only in this format. If you let x be 1 right here, then you'd get negative 1/2 plus 5/2, which is 4/2, which is 2. The point 1, 2 is on this line. Boom, right there, and etc., etc., etc. So x comma y is the form, but whatever y equals, you put that in the spot for y when there's infinite solutions. Next and final graphing one. Let's get y all by itself. The first dude, so let's use red. I like red. Subtracting 2x plus 3. Y is not all by itself because there's a minus. That changes all the signs here. And now let's plot every humanly possible nice, neat point that we can from rising and running. Rise 2, run 1. Do, 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 do. Rise 2, run 1. Down 2 to the left 1. Down 2 to the left 1. Down 2 to the left 1. Then connect the dots, make a line. Next guy, 2y equals a negative x plus 4 divided by 2, negative 1/2 x plus 2, and then that means the slopes, you can look, are not the same, so they're not going to be parallel lines. It's not the exact same equation, so they're not going to be coinciding lines. They'll intersect, and for all you memory fans out there, those slopes are opposite reciprocals. These are actually perpendicular lines. But perpendicular lines are, in fact, intersecting lines. So that's all that we care about in these problems, is where do the two lines intersect at. Well, I'll put my 4 points, and I got a dot on top of a dot right there. So boom, they intersected at the ordered pair of 2, 1. So they were intersecting lines. Also, in the fact they were perpendicular, they intersected at a right angle because the slopes were opposite reciprocals. That has nothing to do with what we're doing, but just bringing back some precious memories. That's solving systems by graphing. First line, plot as many points as you can. Now to solve systems by substitution. Here's how I've always taught it in the past. You would solve a system by substitution if you had a variable all by itself on one side of the equal sign. Well, in this problem, we don't have a variable all by itself on one side of the equal sign, and neither on these. But we still want to solve by substitution, because what we're doing here is we're practicing with linear equations, stuff we are pretty comfortable with. As this chapter moves on, we're going to have all kinds of crazy systems of parabolas intersecting parabolas, circles intersecting circles, ellipses, which you don't even know what they are, hyperbolas intersecting each other. So we need to just learn the basic process of how do you solve a system by substitution. You got to take one of these equations and try to get a variable all by itself on one side of the equal sign. And if there's a variable with a coefficient of 1, oh, like this guy right here, where this x has a 1 right smack dab in front of it, you'd like to try to get that one by itself. That'd be the easiest method. So what I could do right here is say x equals negative 3y minus 6 by subtracting y from both sides. Then I think it's a really wise idea to like cross that equation out. It's like, I have modified you to be this blue guy right here. I don't want to use you anymore. Then I've always taught substitution by this. You know that x equals this, so I'm going to put a box around this. X is negative 3y minus 6. I want to go to the other equation that I have right here, and whatever variable's by itself, I want to put parentheses around that. And I want to say I want to take what's in the box and put it in parentheses. Since this is what x equals, I can let negative 3y minus 6 equal x by substitution. I can just substitute that in. So now I'm going to rewrite this dude, but what's in the box will go in the parentheses. Negative 3y minus 6 is what x is, but everything else gets copied down the same. That's the exact same thing, but where there was an x, I put a negative 3y minus 6. Now this equation is beautiful because all it has for variables in it is y's. So I can distribute the old 2 through and get a negative 6y minus 12, and there's still a minus y equals 9. I got some like terms on the same side. That is negative 7y's minus 12 equaling 9. Add 12 over and get a 21. And then divide both sides by negative 7, and y equals negative 3. There's half our answer right there. We know the y value of where these lines intersect at will be, negative 3. Now to figure out what x is, here'd be a great thing to do. Substitute negative 3 in for y into this equation, and it will tell you what x is. So x will equal, I do just a little bit of work wherever I got room here, so x equals negative 3 times negative 3 is 9 minus 6. I just put negative 3 in for y right there, and then x equals 3. So now I must write my solution as an ordered pair. I'm always a fan of doing this. I always put like a fake answer blank right there, and then say that my solution is at 3, negative 3. Remember, x comes first in the ordered pair, and y comes second. So let's solve this guy by substitution also. I'm trying to get a variable all by itself on one side of the equal sign. So this would probably be the best one. Even though it's not a positive 1y, it's a minus 1y. So I will do this first. I'll have minus y equals minus 2x plus 7, because I subtracted 2x over. And now I know that y equals 2x minus 7, and cross this brother out. The reason why I'm solving this by substitution is because they told me to solve it by substitution. So I will do that. And now that I know that y equals 2x minus 7, I'll put a box around that, and I want to substitute that in for y into the other equation. Because y equals 2x minus 7, that's going to go in for y right here. So what's in the box goes in the parentheses. And we'll distribute that and get 6x minus 6x plus 21 equals 14. And we've got like terms on the same side. It's 6x and negative 6x, which add together to be 0x's. So they cancel each other out. There are no x's over here. You're left with 21 equals 14. Since all the variables disappeared, that means since we're solving linear guys, the idea of one solution has went away. The answer can only be either no solutions or infinite solutions. So we have to look at what numbers are left and see if that's a true or false statement, or I call it a yes or no statement. Does 21 equal 14? Yes or no? Well, that's a no, so I'm going to cross out the equal sign. Since I said no, that means the answer is no solutions. There are no solutions to this situation, because when we solved, all the variables went away, and I was left with two constants that were not a true statement of 21 equaling 14. Solving by elimination is probably the most popular method that we have done. You need all your like terms on top of each other. You need x's on top of x's, y's on top of y's, equal signs on top of equal signs, and constants on top of constants. That's very important that you got equal signs on top of each other. So I'm looking for adding these together and seeing if I can get some variables to cancel out. So I got a 2y right here and a negative 2y. Since those have opposite coefficients, you can add them together and that you will get 0 y's. You will be left with a negative x right here, and negative 2 comes down. If negative x equals negative 2, that means a positive x equals positive 2 by dividing both sides by a negative 1. And now I just need to figure out what y is, so I will substitute x back into either one of these equations. It doesn't really matter. So I'm going to put 2 in for x right here, and I'll get 10 plus 2y equals 12, and solve for y. And now I'll write my answer as an ordered pair. I like it next to the number. If you can do what Mrs. Colwell tells you when she tells you what to do. You can do what Mr. Dreyer tells you when he tells you what to do. But 2, 1 is our ordered pair. Next guy, solved by elimination because they tell me to. I need to get a set of opposite coefficients on top of each other, just like I had a 2y and a negative 2y. Can't add the x's together right now, they won't cancel out. Can't add the y's, so I've got to force them to be canceled by doing a little modifying way of multiplication. I'm going to cancel my y's. I'm going to find the least common multiple between a 2 and a 3, which is a 6, and try to turn one of these guys into a positive 6 and one of these guys into a negative 6. They're already set up with opposite signs, so I can say if I multiply this times 3, that would turn out to be a negative 6. And if I multiply this guy times 2, that would make this guy turn out to be a positive 6y. So I'll multiply right across is how I like to roll, and that would give me a 9x minus 6y equals 12. Don't forget you got to distribute to everything. A lot of people forget to take it times that last guy right there. This brother down here would give me a 10x plus 6y equals negative 50. And now I can add these together and get my variables of y's to go away, and I got 19x equaling a negative 38 when I do that. So I can divide both sides by 19, and that would make x equal a negative 2. And now I can substitute this into any one of these four equations, 1, 2, 3, 4. I'm going to choose one of these to make it smaller. You know, it's got smaller numbers. So if x equals negative 2, I'm going in here. That would give me a negative 10 plus 3y equals negative 25. 3y will equal a negative 15 after I add 10 over. And then finally divide by 3, and y equals the negative 5. I'm putting my ordered pair right here of negative 2, negative 5. X first, y second. Ooh, nasty fractions. I don't like fractions. You don't like fractions. Let's see if we can try to kill two birds with one stone. If this right here is a negative 1y, and this has a fraction in it, I would like to try to cancel these fractions at the same time, but also turn it into the opposite coefficient of this. If this is a negative 1, I would really love for this to turn out to be a positive 1y. Well, to get rid of the fractions, I know I'm going to have to multiply by 2. And if I do that, if I only multiply by a 2, then that would turn out to be a negative y. So how about I multiply by negative 2, and that would make this negative times negative into a positive, and the times 2 and the divide by 2 will cancel each other out. So I'll take this whole bottom equation times negative 2, and I'll get negative 4x plus 1y equals negative 8. Then I like to cross this guy out and just add these two together, the top one and this here bottom one, and see what happens. 4x and a negative 4x, ooh, they cancel each other out, and you get 0x. Sorry. These y's cancel each other out, so since everything over here disappeared, you're left with 0. You can't just put nothing, you have to put a 0. But since all the variables went away, we have to look at what we got when we add them together. We will not have one solution. We will either have no solutions or infinite solutions. It is again down to a yes or no statement here. Does 0 equal negative 2? No. So cross out the equal sign and put no solutions. Meaning these were parallel lines and all that stuff, but we're not doing that on the graph situation. We've solved algebraically and said, oh, well, there's no solutions to this guy. On this one right here, it's kind of like there's a lot of work that we need to do here. We need to clear the fractions on this one. So that means we would have to multiply this guy times 2 to clear the fractions because this nasty brother. But that would turn this guy into a 3y. So what I'd like in this top equation is for that to become a negative 3y. So I'll take the top equation times negative 3. It's kind of some serious mental algebra right there. So what would this turn out to be? Well, that would turn out to be a 3y. Well, I need this to be a negative 3y. So that would give me a negative 6x minus 3y equals negative 24. Right, double check. Yep. And then down here, I'd get 6x plus 3y equals positive 24. So x's cancel each other out, y's cancel each other out. You're left with 0 over here, and now negative 24 and a positive 24 adds together to be 0. So you're left with 0 equals 0. Since all the variables disappeared, we will not have one solution. We will either have infinite solutions or no solutions. So it's yes or no time. Does 0 equal 0? Yes. That means there are infinite solutions. we must put that very fancy answer. Do not write this. Those of you that feel like you want to write this, this is not right. This symbol means infinity, not infinite. So we don't say infinity solutions. It's infinite solutions. You got to write that word out. Okay, no sideways eights or anything like that. So infinite solutions in the form x, comma, I got to know what y equals. Well, that means I got to take one of these equations and solve them for y. I think this would be the easiest one to solve for y. That would make y equal negative 2x plus 8 is what you do. So whatever y equals goes in right here. Negative 2x plus 8 is what y equals, so it goes in the ordered pair right there. So that should be a refresher of how to solve systems with some new information for some of you about this infinite solutions in the form of. I want to make a note though, just because these had fractions in it doesn't mean that all the variables are going to go away. It's just kind of we wanted to shorten this up as possible for a lesson and teach you how to deal with fractions all at the same time. So we kind of put those together and made that happen. So just because they have a fraction in there doesn't mean that all the variables are going to disappear. Your homework is to do the 3-1 worksheet. Let us know if you have any questions, and have a good one.